Chapter 1b, Displaying Distributions with Graphs. So make sure you take time to read through why we're studying distributions and graphs, the learning objectives for this activity, and the vocabulary. So you want to read through all of this before we look at the examples, so now is a good time to pause the video if you haven't read. On the bottom of page 28, there's a note about displaying categorical variables. So we're going to start by looking at bar graphs and pie charts. So these are the two ways that we can display categories. And we say that the categories are mutually exclusive or disjoint because they're not overlapping when we ask a categorical question. So to make a bar graph or pie chart, we need to have each count be in one category or another. So example 1 shows us a pie chart of the LMC ethnic composition from fall 2009. And here where it says N equals 11,056, it's telling us the number of students in fall 2009. So the first question we always ask about our data is, what is the source of this data? So this came from the LMC Office of Institutional Research in 2009. The Office of Institutional Research collects data about students, and the data that we need to report to the state is a community college. So one of the surveys that they conduct is about the ethnic composition. So who is our next question? Who or what are the individuals described by this data? So the individuals in this particular survey are the 11,056 LMC students from 2009. And the variable being measured, the what question that we ask, is the ethnicity of the students. And then what are the values of the variable? So the values are the different choices here that we can assign students to. And you'll notice next to unknown, I put declined to state. That's probably what the unknown category is. So the values are 2 or more races. That's this small pie right here. Filipino, African American, Pacific Islander, Asian, American Indian, Hispanic, Caucasian, and then this unknown or declined to state category. So the values are the different answer choices for the categorical variable. And this is a categorical variable since the ethnicity choices are categories. There's a percent is reported as the outcome, but there's not a number answer that a respondent would give. They would choose a category for ethnicity. And then why? What are some of the questions that could be answered using this data? So you might ask, what ethnicity has the largest population at LMC? How many different ethnicities are at LMC? What percent of students are not Caucasian? Any sort of question related to the variables here would be an okay answer for this. What are some of the questions we could be answered using this data? And then we want to know, does the pie chart show the distribution of this variable? Why or why not? So this is a distribution since we see all possible ethnicities students could have chosen. So remember, to be a distribution, we have to see the whole picture or 100% of the data or all possible answers. If we had just omitted any part of the graph, if we just looked at part of the category answer choices, and it wouldn't be the full distribution. Example 2, this is a 3D bar plot, and it's showing the population distribution of the United States. So what variable is the 3D bar graph measuring? So the variable here is the U.S. cities. So each different city here is one of the values of the variables. The population value is dependent on which city is selected. So if you're not sure what the variable, think about what's the very first thing that would be reported or recorded in a survey like this. And some of the values the variables might take on are these different cities. So San Francisco over here would be a value. Los Angeles, I'm assuming the big spike on the West Coast is Los Angeles. New York, the big spike on the East Coast. Boston, Santa Fe down here, right? These are all values that the variable cities in the U.S. could take on. What type of variable is this being measured? Cities are categories, so this is a categorical variable. The bar graph, anytime we have a bar graph, that corresponds with categorical variables. And then the heights of the bars in this key that we see here at right are listed in scientific notation. So what does this mean if we say 1.5 E7? So in scientific notation, E7 means you're moving the decimal point 7 places larger. So if we move the decimal point over, 1.5 E7 is 15 million for the population. So I'm guessing that's New York or Los Angeles might be that bar height. I'm guessing maybe New York. I think Los Angeles is not even 15 million people in the greater Los Angeles area. So something you can go look up on Wikipedia, the populations this year. And then what trends do we notice about the population in the U.S. from studying this 3D bar plot? So not just looking at the bars by the city, but the geography as that third dimension. So we can see high population cities are clustered on the West Coast and the East Coast. The Midwest and the Southwest look to have some medium-high population cities. And then the west or central part of the U.S. does not have very high population cities out here. So this is the West Central. We see the South has some medium high population cities. It looks like the Midwest has some high population cities, but there's a big concentration on the coast. Example 3, these are results from a Gallup poll. And then we're told that the results for adults are based on telephone interviews with a randomly selected national sample of 1,000 adults 18 years or older from April 2001. The results for teens are based on telephone interviews from a randomly selected sample of 501 teens between the ages of 13 and 17, conducted March through May 2001. So our very first question is, what's the source of the data? That should always be the first thing we look for. So we see this came from the Gallup polling agency and that the data is from 2001. And then who? That's our next question. So who or what are the individuals described by this data? So it's adults and teens throughout the United States, and we can be specific and say, 1,000 adults were in the sample and 501 teens were in the sample. And then there's two different tables here reporting the data that they collected. So we see one of the variables up here is the self-description of health. And then the second table has things that were done that were not good for the health. And in the second table, they were able to check multiple boxes. So it's important to notice that the counts, if you were just going to add up the counts, some people checked more than one box, so the total would be more than 1,000 for the adults and more than 501 for the teens. And similarly, the percents total more than 100 because there's multiple checks going on. Whereas this first question only had choose one option, so these percents should total 100%. So I drew arrows for the values in the table. So these arrows for self-description of health going to excellent, good, just, fair, and poor, those are all the value choices. And similarly, all these answer responses where we drew the arrows are the values of things that are not good for their health. So these are categorical variables, since the answer choices that someone would have in the survey are categories, not numerical values. They're not reporting how much alcohol they drink or how many hours they sleep. They're just checking off these categories if they apply. And then you could only represent that top table, self-description of health, with a pie chart since the total is 100%, right? It wouldn't make sense, since some people are counted more than once here, it wouldn't make sense to use a pie chart in the things I have not done good for their health check boxes. So if we wanted to draw a bar graph to compare adult and teen responses, should we use the counts in the table or translate the counts into the percents? So since there were 1,000 adults and 501 teens, not the same amount in each group, it's preferable to compare with percents for interpreting differences. Anytime we compare different size groups, we want to use a percent or a proportion, and the proportion can be the fraction or the decimal. Often we'll see things like we're going to compare groups of 100,000 people if we're comparing people in different states or different cities, because we want the same denominator in our fraction proportion to compare. Example 4 gives us a table from Consumer Reports in 2016. So Consumer Reports here is comparing which brands make the best cars. So we see we've got a table here with rank, the make, the overall score, the road test score, the predicted reliability, and the percent recommended test models. So presumably they had some sort of weighted formula for determining rank based on these four rankings and categories that they gave. So our very first step is to understand what's the source of the data and when was it gathered. So this is Consumer Reports magazine. It's from 2016, so it's recent. And then who or what are the individuals described by this data? These are car brands. So if you'll look, maybe car make is a better way to say what we're describing. So they're not talking about specific models, but the overall brand or make of the car. And then what are the variables being measured? And then which of these are quantitative and which are categorical? So the overall score, that's a number. So we said it's a quantitative or a numerical variable. Quantitative and numerical can be used interchangeably as terms to describe variables. Road test score, that's quantitative / numerical. The predicted reliability, notice we've got these circles that are shaded in different ways. So those are categories where the circle with the dot in it corresponds to excellent, and then the solid circle corresponds to poor. Usually we say excellent, very good, good, fair, poor. There's a key on the next page. And then percent recommended test models, that's a percentage, so that's a quantitative or numerical variable. So then we ask why. What's the question a consumer might answer using this data? So I came up with which overall score range is most popular, how many car brands have very good or excellent reliability. These are things I might want to know as a consumer thinking about a new car. So now in part B, we want to construct a bar graph. So I'm going to show you how to do that in StatCrunch. So here in StatCrunch, I have typed my categories. Predicted reliability is the variable, and then my values are excellent, very good, good, fair, and poor, and these correspond to the shaded dots. And then in the count column, I counted up how many times each of these dots appeared in the table. You'll notice this next column over here is the percent recommended, so this is a quantitative variable. I'll come back to it a little bit later. So when we're entering the data like this, we say this is a summary because I didn't enter every single car and its rating. I just entered the summary data. So when I make my graph, we go to graph, pie chart, and then we choose with summary. If I had entered every row in the table, then I would have used with data and had it pull the data from the table. So the categories lie in my predicted reliability column, and the counts are in the column I called count. And then by default, notice both count and percent total are highlighted, so I'm going to leave those both highlighted. I'm not going to build any sort of relationship, so I'll leave that blank for now. Color scheme, I'll leave it basic now, and I'll show you how to edit it. And then I want to give my graph a title, so I'm going to title it Predicted Reliability. And compute. And now I made a pie chart, but I think I was supposed to make a bar graph here. So if I want to make a bar graph, I should go to graph, bar plot, again with summary, and my categories are predicted reliability, my counts are in count, and then you can order it however you want. I'm going to order like the worksheet as it, so that should keep the same order I typed it in. And then let's see if I want to give it a title. I can give it a title, predicted reliability. And then on the bar graph, I can label the x-axis and the y-axis. So I'm going to label the x-axis as predicted reliability category. And you'll notice StatCrunch even will autocorrect your spelling typos. And then the y-axis I'm going to label as count and compute. And so here's my predicted reliability. And we see a spike of good just like we saw in the pie chart. And then if I want to make it look a little bit more interesting, I have color options. So let's see, this is the basic color scheme. I can adjust it to be maybe the many shades. Let's see how that one looks. And it's just giving me the purple here, but you can go in and adjust things to color different colors. So what's nice about the bar plots in StatCrunch is that if you hover your mouse over, you can see exactly the frequency, which is telling us how high the bar is, and that corresponds with predicted reliability good. If I come and hover over the very good category, I can see the frequency is 6. The pie chart gave me a key over here, but again, I could do the same thing. So I could go to the very good category, hover my cursor over, and it'll tell me there are 6 very good ranked cars, and that's 20% of the total. So the pie chart also calculates the percentage. You can double check if you add it up, it should total 100%. So pie charts look nice, but in terms of sketching, the bar plot is a lot easier to sketch. So that's why in your workbook I said sketch the bar plot there. So you could either paste a screenshot in or go ahead and recreate a sketch here. Then we're asked to describe what we notice from this distribution. So if we look back at our StatCrunch trends here, whether we're looking at the bar plot or the pie chart, we see that good predicted reliability category had the most number of cars, excellent had the least number of cars. And you could say, you know, fair and very good both had middle amounts. So now, how do we display numerical or quantitative variables? So for these variables, we use histograms and stem plots. So in a histogram, you're not going to see the names of the individual people, but you're going to categorize by the number range or the bin size. Sometimes these are called classes also, so class or bin. So the horizontal axis typically shows the variable values, and then in the stem plot, you're going to have each number entry representing an individual. So the first thing we do here in example 5 is create a frequency table for the distribution of percent of recommended test models. So I went ahead and broke up the bins by percentages. So to go all the way up to 100%, the bins go from 0 to 19%, 20 to 39%. So we're counting by 20s. This is a typo here. It should say 80 to 99%. And then I wanted 100% in a bin by itself. There's no scores over 100%. If we did go over 100%, this could go from 100 to 119%. But I wanted to see how many had perfect scores. So here's a sketch with the frequency on the y-axis and the percent recommended test models on the x-axis. So this corresponds to my bin values, the percentages, and my frequency is the height of the bars or the y-axis. But let's go look at how we can describe this using StatCrunch. So if we head over to StatCrunch, you can exit out of your graphs, and your results are always saved up here under StatCrunch. So if you go to StatCrunch results, when you exit out, you just click on pie chart or bar plot again, and your graph comes right back. So now I'm going to go to graph, and I'm going to come down to histogram, which is the kind of graph we use for quantitative data. And notice the only columns here that I can choose from are the ones with numbers. The predicted reliability categories over here are not an option for me. So I'm going to choose a percent recommended test model column. And this column is just typing all those numbers from the consumer reports table. It's not necessary to sort the table. You could, but StatCrunch will sort for us. And then we want to tell us how wide to make the bins. So I want my bins to start at 0 and count by 20, so that that first bin goes from 0 to 19, and then we go from 20 to 39. And I'm going to say compute. And so we see here is the histogram, and this looks just the same as what I drew on our paper using the frequency table. If we hover our mouse over, it'll tell us that first bar from 0 to 20 has 7 cars counted. And notice when it says percent recommended test models, the 0 has a square bracket, but the 20 has a parentheses bracket. So that square bracket is telling us that this bar includes values as low as 0, but it only goes up to 19%. The 20 is in the next bar. And so see how there's a square bracket on the 20 in the next bar. So this very last bar goes from 100 to 120. We know the highest value in our table is 100. So this frequency of 3 is capturing the 3 car makes that got 100% recommended test models. In options, you might have noticed we could have checked markers for the mean and the median. So the mean is the average. So if I want to see what's the average, I can check that box, and when I compute, I can hover my mouse over this green bar and it tells me the mean or the average is 44.9. So that's the average of all of these cars in the list. Another way to do that is you can go to Stat, Summary Stats, Columns, select percent recommended models, and then just select mean and compute. And you can see StatCrunch computes the mean is 44.9, which is the same result as if we hover our mouse over here. So we would describe this distribution as skewed to the right because it's got a bit of a right tail out here. You can see there's a high peak from 0 to 40% recommended test models. There's a little bit of a peak from 60 to 80, and then fewer cars have scores 80 and higher. Now we want to draw the stem plot, and we can do that using StatCrunch or drawing it by hand. So let's go look at how we do it in StatCrunch. So I'm going to exit out of these, and remember, they're not gone, they're just over here under StatCrunch results, so you can always open things back up. And we go to graph. Stem and leaf plot is what we call a stem plot. I choose my column, percent recommended test models. In leaf unit, I'm going to leave it optional, and we're going to see how they take care of the leaves. So the leaves are the tens place. See how by default they did leaf unit 10? And then when there's a lot of data, what StatCrunch does is it separates it by fives. So the first row here are all the values from zeros to 4. So this is from anything from 0% up to 40%. And then this is anything from 50% to 90%. And then this last row are the 3 100s. And if you rotate your head, you can see, oh yeah, this has a right skew going from smallest to largest. Now let's go edit our leaves and have our leaves group by 1s instead of 10s and see what happens. So you can see this is looking more like the bar graph, except the bar graph was counting by 20s, so these were all in one bar here from 0 to 19, and similarly these were in one bar from 20 to 39. But we still sort of see that overall right skew here if you imagine rotating your paper and then kind of drawing the curve over the data. You see a tail out here to the right. So when we compare and contrast the two graphs, we can say although the bin size is different in the stem plot, the shape is still skewed to the right. And with the stem plot, if I'm not specific, you have the option to set your leaf unit to whatever is reasonable. So in this case, it would be reasonable to count by 1s or to count by 10. So when we're counting by 1s, what this is saying is these are all scores of 0. This next row, this would be a 1 and a 7, meaning this was a score of 17. There was another car that had a score of 17. If we come to the 2 rows, this means there was a car make that had a score of 20, a car make that had a score of 25, another 25, another 25, a 27, and a 29. So each value in here counts as a car make. So notice 25 came up 3 times. If you look back at the table, you see it came up for 3 different car makes. So we've got to put all 3 of those 5s in there because we want to make sure that it is representing each different brand is being counted, or each different make is being counted. StatCrunch automatically sorts the data for us. If you're drawing your stem plot by hand, at this point you don't have to sort the data. You could still see the overall shape even if you put these down in the order you were writing them and not in numerical order. So for example, if I was going down the list, I would have 88, so I'd stick an 8 here, and then another 88, I'd stick an 8 here, and then the 80 comes up here in the middle, so it would have gone 808. It wouldn't be sorted nicely like StatCrunch, but I could still see that the bar height was 3 there. Later on, we are going to sort it, so it's a good idea to practice sorting it like StatCrunch.